All right, today we are going to dive into two of the most, and I mean most, fascinating families on the entire periodic table, the alkali and the alkaline earth metals. These guys are so important, not just for the world around us, but for the chemistry that's literally happening inside our own bodies. So let me ask you something to get started. What do you think fireworks, the battery in your phone, and your own bones could possibly have in common? I mean, they seem totally unrelated, right?
Well, the answer is all about chemistry. Specifically, every single one of them depends on the really unique properties of Earth's most reactive metals, which are exactly the ones we're going to get into today. Okay, so to really understand these elements, we first have to figure out where they live. So let's pull up the periodic table and find their address. First up, all the way on the far left, that very first column, that's Group 1, the alkali metals. This family has some pretty famous members. You've got lithium, sodium, Na, and potassium, K, running all the way down to francium, which is just unbelievably reactive. And right next door, in column 2, are their slightly calmer cousins, Group 2, the alkaline earth metals. This is where you'll find elements like beryllium, magnesium, and calcium. And trust me, it is no accident that they're neighbors.
So what is it? What makes these two groups so special, so eager to react with everything? Well, the whole secret to their personality, it all comes down to something called valence electrons. The alkali metals over in Group 1, they have exactly one, just one, solitary electron in their outermost shell. That number, 1, is the key to everything. And if you look at their neighbors in Group 2, the alkaline earth metals, yeah, you can probably guess the pattern here. They have 2 valence electrons. And that tiny 1 electron difference, it changes everything. So what are these valence electrons anyway? Well, you can think of them as the atom's social electrons. They're the ones hanging out on the outer edge, and they're the ones that control how an atom is going to interact and bond and react with any other atom it bumps into. And here's the most important part. Atoms are all driven by this one basic desire. They want to be stable. And for an atom, stability means having a completely full outer shell of electrons. So for these metals, the absolute easiest way to get to that happy place is to just get rid of those 1 or 2 lonely electrons. So let's see how this actually plays out by taking a closer look at Group 1. Their defining trait? They are desperate to give away that 1 electron, and that desperation makes them soft, shiny, and just explosively reactive. I mean, the members of this family are like the rock stars of the periodic table. They're so reactive, you can't even leave them out in the air. They have to be stored under oil. And they're so soft, you can literally cut them with a knife. And because that 1 electron is so ready to jump ship, they are fantastic conductors of electricity. And if you want to see just how extreme this gets, check this out. If you take a tiny piece of sodium and just drop it in water, it doesn't just fizz. Oh no, it can actually skate across the top of the water, releasing so much heat and hydrogen gas that it can burst into flame or even cause a small explosion. That is pure chemical desperation right there. Okay, so now let's go meet the neighbors, the alkaline earths. They've got that same family passion for reacting, but here's the thing. They have to get rid of 2 electrons instead of just 1. So they're just a little more chill about it. So while they are definitely still considered highly reactive, they're a clear step down from the alkalis. They're also harder and denser, but they're still great conductors. And since they lose 2 electrons, they end up forming ions with a +2 charge. And we see these elements everywhere. That super bright, blinding white light you see in fireworks, yep, that's magnesium burning. And calcium, it's the essential building block that makes our bones and teeth so strong. So this brings up a great point. How do we actually use all this reactivity in the real world? This constant eagerness to give away electrons isn't just some cool science fact. It's an incredibly powerful engine for all sorts of technology and for life itself. And what's really cool is there's this fascinating trend inside each group. As you go down the column, the atoms themselves get bigger. That means those outer valence electrons are getting farther and farther from the nucleus, so they aren't held on as tightly. The result? They're even easier to give away, which means reactivity actually increases as you go down the group. So yeah, these elements are truly all around us. Lithium's eagerness to lose an electron is what powers our rechargeable batteries. Sodium hooks up with chlorine to give us table salt. We get calcium from milk for our bones.
Magnesium helps settle our stomachs in antacids. And strontium is what gives fireworks that brilliant red color. Okay, let's bring it all home with a quick final showdown. We're going to do a side-by-side comparison to really lock in the key differences between these two families. And here it is, the ultimate cheat sheet. You've got group 1 versus group 2, 1 valence electron versus 2, a +1 charge versus +2, very high reactivity versus just high, and super soft metals versus harder ones. You see, the whole story is right there in the numbers. So if you remember one thing from all this, let it be this. An element's address on the periodic table is basically its destiny. Just by knowing what group it's in, you know its valence electrons, and that tells you almost everything you need to know about its chemical personality. So now that you know their secrets, start looking around your own world, from the salt on your dinner table to the smartphone in your hand. Where else are these super reactive elements hiding in plain sight?